Hello everyone, I Dr. Kirti Sahu welcome you all to this learning video on numerical method. Dear learner, as we have seen that many problems in science and engineering can be reduced to the problems of solving differential equation satisfying certain given conditions. By applying analytical methods, we can solve the several standard types of differential equations which we have studied in the previous classes. So, however, the differential equations appearing in the physical problems are quite complex and may not possess the analytical solutions. So, in such cases, there is a need of solving the differential equation numerically. So, we know that the general solution of any differential equation of nth order is containing the n arbitrary constants. So, in order to compute the numerical solution of such equations, we need the n conditions. So, if all the n conditions are specified at the initial point only, then it is called as a initial value problem, and if the conditions are defined or mentioned at two or more points, then such problems are called as a boundary value problems. So, we are going to discuss here the numerical solution of initial value problem and obviously of first order. So, the problem which we are going to consider is of the form dy by dx is equal to f of xy with only one conditions given at initial point. So, these problems can be solved by any of the methods, and basically these methods are of the two form. One is a power series method where a series for y in terms of x is given and from which the values of y can be obtained directly by the substitution. So, the Taylor series method and Picard series method belongs to such types, whereas in the other methods the tabulated values of x and y is given, and by using the iterative process such as Euler, Runge-Kutta, Milne predictor, one can obtain the solution. So, in the series method, the y is approximated by a truncated series and each terms of the series is a function of x, and hence these information gives the value of gives the information about the curve at one point, and the solution is not iterated further. Hence, the power series methods are called as a single step method or a pointwise method, which we are going to discuss here. So, in this video lecture particularly I am going to discuss the Taylor series method. So, let us see what is Taylor series method. So, we will consider a first order differential equation, say dy by dx is equal to f of xy with y of x naught equal to y naught. So, we know that the Taylor series expansion of function y equal to f of x at x equal to x naught is given by y of x is equal to y of x naught plus x minus x naught y dash of x naught plus x minus x naught whole square by 2 factorial y double dash of x naught plus up to. So, here number of terms can be written, but here in this video lecture we will find out the Taylor series expansion up to fourth order derivative only unless and otherwise specifically mentioned in the problem. Now, here if x naught is 0, then this problem can be reduced to, or this formula is reduced to this form. Now, as y is equal to f of x, so sometimes the formula can also be written in this form. So, these are the various forms of the Taylor series expansion which we are going to use here. So, remember, Taylor series method is nothing but a single step method and it is a power series method for solving the first order differential equation where the initial condition is given, that is the initial value problem. So, let us try to understand this method with the help of the problem. Before that, you should know what are the drawbacks of the Taylor series method. So, Taylor series method though is a powerful single step method, but if we are able to find the successive derivatives. So if you observe the formula over here, so y dash, y double dash, y triple dash, all these are nothing but the derivatives of y. So if we are able to find the successive derivative easily, then Taylor series method is considered as one of the powerful single step method. But if suppose f of xy involves some complicated algebraic structures, right, then the calculation of higher order derivatives becomes tedious and eventually the method fails. So this is the major drawback of this method. Otherwise this is very useful for finding the solution of first order differential equation. Also, apart from having this drawback, this method is considered as the one of the useful method for finding the starting values for the other methods as well, that is the multi-step method or the step-by-step method such as Runge-Kutta method, Milne's method, etc., which we will discuss in the upcoming video lectures. So let's see how this method applies and how to get the answer. So if dy by dx is equal to 1 plus xy, given y of 0 equal to 1. So this is the initial condition given. Here it is mentioned that you have to write the series solution up to first 4 terms by Taylor series method. So here we are going to see when we shall get the first non-zero terms, 4 terms in the series expansion. Also we have to find out y of 0.1 and 0.2. So what we will do, so this is a given condition, we will compare it with the standard form of differential equation. Just recall what is the standard form of differential equation. So standard form of differential equation is nothing but what, dy by dx is equal to f of xy and y of x naught equal to y naught. So if I will compare this with this standard form, so what I will get, I will get f of xy, what it will be, 1 plus xy. Again comparing the conditions, so what I will find, I will find x naught as what, 0 and y naught is equal to 2. In this way we will find out these required quantities. Now after this we will write the formula for Taylor series expansion at x equal to x naught. As I said, if it is not given then we will write up to 4 terms, but here as it is mentioned, write up to first 4 terms. So obviously we will see whether we have to go up to the third degree term, order derivative term, or fourth order derivative sum. That depends upon the value of the derivatives. So obviously if suppose some of them become 0, so we will have to obviously calculate the fourth order derivative terms. So that depends upon the what are the values so obtained after simplification. So what is the requirement of this formula? We want y at x naught, y dash at x naught, y double dash at x naught, y triple dash at x naught, and so on. So let's find out this one by one. So here one of the value is already given. What is that? Y of x naught. Y of x naught equal to what? Y naught. Y naught is already given, that is 2. So the first value is coming out to be non-zero, so that is 2. Now again one more thing is given, that is what, dy by dx, which is nothing but denoted as y dash of x, which is equal to 1 plus xy. So I have to find out its value at x naught. So what will be y dash at x naught? Y dash at x naught is nothing but equal to 1 plus, so what we will do, everywhere as I know that y at x naught is denoted by what, y naught. So everywhere when we will put x as x naught, in that case y will become y naught dash will become y dash at x naught becomes what, y naught dash. So this one should remember, right? So what I have said, I am going to repeat this again. So when I will put this value of x as x naught in this derivative terms, so obviously x will get replaced by x naught, but the value of y at x naught as per this notation is what, y naught. So y at x naught is y naught. So in the similar line, y dash at x naught will be denoted by y naught dash. Okay. So what we have? So 1 plus x is replaced by x naught, y is replaced by y naught. We know all these values. Let's substitute them. So we have 1 plus x naught is 0, y naught is 2. So this becomes 0. So what we have? Y dash at x naught is 1. This is also non-zero. So I am getting how many non-zero terms? I am getting 2 non-zero terms. I need 2 more, right? So let's call these equations one by one as 1 and 2. This is going to be used in formula number A. Now we have to find out the derivatives. Why? So far the values have been obtained directly with the given information. Now I have to find out the second derivative. So what I'll do, I have to differentiate this equation 2, right? This equation 2, what is that? Y dash of x is equal to 1 plus xy. This we will differentiate to obtain y double dash. So what it will be? The derivative of, see, the derivative of 1 will be 0, and here we will apply product rule. X into y, applying product rule. So x as it is, derivative of y will be y dash, plus derivative of x is 1 and y as it is. In this way the differentiation is done. I hope you must have understood this. Here we have applied product rule to differentiate. Differentiate what? Y dash is given as here 1 plus xy. So this I have differentiated. Okay. So derivative of 1 is 0, and here applying product rule, x as it is, derivative of y is what? Y dash, plus derivative of x is 1, y as it is. Okay. Now let's find out its value at x is equal to x naught. So just replace x by x naught and the corresponding terms of y by y naught. So it is y naught, y dash will become y naught dash. We have the value of y naught dash. In the previous term equation we have got this value as 1. So we will substitute this as 1. Y naught is 2. So in this way I am getting the second derivative also a non-zero, right? So in this way I am having now 3 terms. Now let's differentiate one more, so to get the third order derivative. So differentiating this x y dash plus y with respect to x. So here we will apply product rule. So x derivative of y dash is y double dash, plus derivative of x is 1 and then y dash as it is. Okay. Then next derivative of y is y dash. So this simplifies to these two will get added. So we have 2 times y dash. Now let's find out its value at x naught. So what it will be? X naught y naught double dash plus 2 y naught dash. Putting the all values required over here. So x naught is 0, y naught double dash is 2, plus 2 times y naught dash is 1. So in this way I will get 2. So how many terms we are getting so far as non-zero? Y is 0, y is non-zero, y naught is also non-zero, y naught double dash is also non-zero, this is also non-zero. So I am getting 4 terms. So I will not calculate the derivative further. I will just put this in the what? The Taylor series expansion that is given in equation A. So just putting the values in equation A, you can see what is the equation number A. So here we have to just put the value of y of x naught, which is 2, y dash of x naught, which is 1, then y double dash of x naught, which is also 2, like this, right? So putting the values in equation number A, what we have? So we have 2 plus x minus x naught is 0, y naught dash is 1, plus x minus x naught is 0, whole square by 2 factorial, y naught dash is 2, plus and like this. Simplifying, and we get this as a Taylor series expansion. So if this question would not be to find out y at point 1, so then this can be considered as the solution of given differential equation with the boundary conditions. But apart from this, what it is asked? It is asked to find out the value of y at x equal to 0.1 and 0.2 also. So what we will do? One by one put x as 0.1 in this formula B and 0.2 in this formula B again. You will get the corresponding values. So what we have? Y of 0.1 as 2 plus 0.1 plus 0.1 whole square plus 0.1 whole cube by 3. So this gives me the approximate answer as 2.1103. Now why this will be approximate answer? Because here we have truncated this series to certain number of terms. We have not evaluated all the terms of the series. That's why this would be considered as a approximate solution of the differential equation, whereas analytical methods gives us the exact solution of the differential equation, which we have studied in the lower classes. So this is a drawback of numerical method, that it gives us the approximate solutions, not the exact solution, right? So I hope this problem is clear to you all. Now let's have the next example. So here also we have to solve the differential equation and have to find out the value of y at x equal to 0.1. So let's start with the given information, then find out the required information, that is f of xy x0 and y0. I hope you know very well how to find out f of xy. So we just have to compare a given differential equation with a standard differential equation, which is always dy by dx is equal to f of xy and y of x0 equal to what? Y0, right? So comparing this given differential equation with this form, what I will get? F of xy is equal to x square y minus 1. Then with this condition, if I will compare, so what I am getting? x0 0, y0 is equal to 1. Don't draw the conclusion that x0 is always 0 and y0 is always 1. This is by default. Here I am getting in the second problem also x0 as 0 and y0 as 1, but it is not the generalized case. Don't generalize this. Okay, now Taylor series expansion we will write over here. Now here no restriction as such is given. So remember, when though no restrictions are given in a problem that find out up to third derivative term or first four terms like this, in that case we will do the calculation up to fourth order derivative terms, which I have written here, right? So here we will go up to the fourth order derivative term. So let's find out how it can be done. So y at x0 is equal to y0 is given. This is y0, which is what? 1. Again, one more thing is always given. What is that? The derivative, first derivative, which is a given differential equation. So dy by dx is y dash of x, which is x square y minus 1. From this, just put x as x0 and get its value. So you will have y dash of x0 is equal to, just substituting all the values required over here, you will get this as minus 1. Now next, before getting the next value, that is y double dash of x0, I have to differentiate this to get the first derivative, second derivative, right? This is first derivative. So just differentiate this term, you will get the second derivative. So differentiating, obviously derivative of 1 will be 0, but here we will have to apply product rule. So let's see how it can be done. So x square, derivative of y will be y dash, and then derivative of x square will be 2xy as it is, right? Differentiation done. Then put the value of x as x0 and simplifying, you will get it as 0. Let's have the next term. So before that, differentiate this expression x square y dash plus 2xy. Now sometimes students commit the mistake, instead of differentiating this expression, they try to differentiate this one, and this is always a constant term. So this always gives you 0. Remember, this is not a function of x, right? So be careful what to differentiate, where to differentiate, how to differentiate. So this is a function of x, this is to be differentiated. Okay, now differentiating, here we apply product rule, here also applying product rule and simplifying. So we get third derivative as x square y double dash plus 4xy dash plus 2y, and then putting x as x0, x0 is a constant value, right? Accordingly the value of y and y0 dash, y dash, y double dash will get replaced by y0 double dash, y0 dash and y0, right? Simplifying, we will get this as 2. So in this way we have calculated third derivative. We have to find out one more derivative terms. So let's differentiate this third derivative expression with respect to x, so and then finding its value. So I hope this process is clear to you all. You must have understood very well the differentiation part as well as evaluation of the derivatives at the given value of x, which is what? x0. So in this way all the derivative terms, this is nothing but a fourth derivative, right? Here it is by mistake written as 4, it must be 3, it must be fourth derivative at x0. Okay, now so putting all these values in equation A, that is using equation 1, 2, 3, 4 and 5, equation 1 for y at x0, 2 for y dash at x0, 3 for y double dash at x0, 4 for y triple dash of x0 and 5 for fourth derivative of y at x0. So putting all these values in the equation A, we get the series expansion for the function as this one. Now as it is required to find out the value of y at x is equal to 0.1, so just put x as 0.1 in this equation number B, you will get the required solution as per the Taylor series method. So I hope this process are clear to you all. Let's see one more example where you'll see what is the difficulty level and what is the difference. So solve dy by dx is equal to with condition given by Taylor series method. Here we have to evaluate the value of y at x equal to 0.1 and 0.2. So this problem consists of two parts. First, to get the solution by Taylor series method, means to get the Taylor series expansion, and the second is its value at x equal to 0.1 and x equal to 0.2. So given again differential equation, comparing it with a standard form, we get f of xy is equal to, here it is wrong, it should be 2y plus 3 times e raised to x. This is our f of xy. Again condition given is y of 0 equal to 0, so x naught is 0 and y naught is 0. Let's write Taylor series expansion. Let's find out the value one by one. So y naught is given as 0 in the problem itself. Y dash is given as 2y plus 3 e raised to x. What will be its value at y naught? So y dash of x naught is y naught dash, which is equal to 2 y naught plus 3 e raised to power x naught. Now when we put y naught and x naught here, so it is 2 y naught is 0, so 0 plus 3 e raised to power 0. E raised to power 0 is nothing but 1, right? Remember here the value of e raised to power 0 is 1. So that's why it is 3 into 1, that gives me 3. Okay, so derivative is, first derivative is 3. Now again differentiating first derivative term with respect to x. So what will be the derivative of this 2y? It will be 2y dash, and derivative of 3 e raised to x is 3 e raised to x. So the differentiation part is very easy here. Just find out its value at x naught. So 2 times y naught dash, we have evaluated this as 3 plus 3 into again e raised to power x naught, that is e raised to power 0, which is 1. So into 1. So how much we are getting here? The value of second derivative at a given point, it is nothing but 9. Let's find out third derivative, and on the similar line the fourth derivative as well. So after evaluating all the values, let's put all the values in the Taylor series expansion that is given by equation A. We get y of x is equal to, so this is nothing but the answer for the solution of the differential equation using Taylor series method. Now we have to find out the value of this at x equal to 0.1 and 0.2 also. So that's why just put x is equal to 0.1 in this formula B and 0.2 in formula B. So we will get respectively the values as y of 0.1 equal to 0.3487 and y of 0.2 equal to 0.811. So I hope you must have understood the method very well. This is the one of the easiest method to obtain the series solution of a differential equation, with only one drawback, that if the function involves the complicated algebraic structure, then you find it difficult. The method is clear to you all. In the next video lecture, we shall discuss another power series method to solve the differential equation, which is called as a Picard series method. So we will see what is the difference between these two series method and which one is the best to apply or to obtain the solution of the first order ordinary differential equation with given condition. So thank you all for watching the video.